Next presentation will be by Professor Shankar Subramaniam. Shankar Subramaniam is an associate professor in Iowa State University. He obtained his BTech from IIT Bombay, MS from University of Notre Dame, and PhD from Cornell. His research interests are spray modeling and simulation of gas particle flows, granular flows, combustion reactive flows, mixing stochastic models. I request Professor Shankar Subramaniam to deliver his presentation.
Good afternoon, everyone. I hope you're enjoying IIT Madras. It's my first visit to IIT Madras, and I have to say it's a fantastic campus, very beautiful. And I really like the deer coming around when you're having breakfast in the guest house. I think that's pretty neat. Okay, so I'm going to talk today about modeling and simulation of multiphase flow and change gears a little bit because that movie that is shown there is actually a gas-solid flow. But what I have to say will hopefully have some relevance to atomization and liquid gas flows as well. So to get started, I'd like to first acknowledge, I'd like to thank Paul Soika, who's not here, but he was very kind to invite me to this thing. And of course, Mahesh and Sujit for inviting me, and the IUSSTF for putting this together. As I was preparing this talk, I thought Mahesh said he'd like to have a broad-based input from other people at the US. So I talked to a couple of collaborators, Brian Hellenbrook at Clarkson, Olivier Desjardins, who's now at Cornell, and Sean Garrick, who is at University of Minnesota, and you'll see some of their comments interspersed in this perspective. I'd like to acknowledge also my collaborators, Rodney Fox, who is at Chemical Engineering at Iowa State, Sundaresan at Princeton, and Christine Hanya at Colorado. And of course, many graduate students have contributed to the things that I'd like to say here, particularly Madhu Pai. He's now at GR&D, worked on some spray work. And Rahul Garg also worked a lot on Lagrangian simulations, which I'll refer to. And the simulations you saw in the first part, the direct numerical simulations, particle resolved, are due to Sudhir Tenetti. And Chris Schmitz has worked a little bit on primary atomization, but I may not get to talk about that today. So in this outline, what I'd like to do is, first of all, I'd like to give you an idea of what are the challenges in modeling and simulation of multiphase flows. And I think that's important because when we start off, it's always good to know what is the beast you're trying to tame, right? So if you don't know what the challenges are, then you may be setting yourself up for more than you can handle. Once I'm done with that, I'll then come up with a framework for representing and modeling multiphase flows. So in this, what we look at is we'll look at principal modeling approaches, and I'll try to compare them. And then I'll try to give you an outlook as to what, in my personal and probably biased opinion, is going to be the future. And you can feel free to disagree, and I hope it'll stir the pot and we'll have some good discussions. I'm going to do the same thing for multiphase flow simulations, in which I'm going to come up with a framework, and then we're going to look at some popular simulation methods, and we'll try to compare them. We'll try to see where do they work, what are they good at, what do they not do so well. And then I'll similarly give you an outlook, which I hope will provoke further discussions. So let's get started with challenges in multiphase flows. The first thing is randomness in the configuration of the dispersed phase. You saw this in the first talk that Professor Raghunandan gave. He showed the spray patternation images, and there's a lot of variability, statistical variability. If you look at a riser flow like this, so this is a vertical channel in which there are particles, and you can see interesting structures of the dispersed phase. This is volume fraction of the dispersed phase. And if you really look at one of these, zoom into one of these, you would in fact expect to see different configurations of particles. And what you're seeing here are actually particle resolved DNS. So this is flow over all the particles is completely resolved. You've got no slip, no penetration at every particle surface. Full Navier-Stokes is being solved. And so each of these contributes to an ensemble that is averaged to produce a structure like that, okay? So the point that we want to take away from this is that the configuration of the dispersed phase is random, and so you need to represent it using some sort of a number density. So it's logical to use a statistical approach, right? Now, we already have encountered statistical approaches in single phase flows. You know that in a single phase flow, if you increase the Reynolds number, you're going to go into transition, you'll have turbulence, and so we already know there's one kind of nonlinearity. What is interesting in multiphase flows is even for a laminar flow, the configuration of the dispersed phase can be different, and so it warrants a statistical approach. So laminar multiphase flows are hard to solve. So I think that's the first point I want to make. If you think single phase turbulent flows are hard, laminar multiphase flows are as hard, if not harder. The next point I'd like to make is that there is other kinds of nonlinearity in multiphase flows. So for instance, if you look at a bunch of particles or droplets, each of them has a velocity, they have an acceleration, and all of these would have some mean, so I'm calling this VSM as some average solid velocity, right? Now, there is a distribution of velocities, which I can call f of v, some probability distribution. And if you actually look at, this is data obtained from particle dissolved DNS. And so we have here a mean Reynolds number of 20 based on this mean slip velocity. And volume fraction is 20%. And what we're looking at here, these points are basically different particles. Each of them has a different velocity. This is the fluctuating velocity relative to the mean. And each of them has a different acceleration corresponding to that individual velocity. If you look at this scatter and you try to fit, suppose you use the standard drag law. Suppose there's a drag law due to Hill and Koch for solid particles. And if you plotted this drag law, you would not recover this scatter. So the point is that the drag law calculated at the average velocity of the particles is not the average force experienced by the distribution. This is because of this nonlinearity that I talked about. This is a very important point. So it means that if you close things at the mean velocity, you're probably not going to get the right answer, right? So this is direct evidence that you need to include the nonlinearity that arises from the fact that the drag on a particle is a function of velocity, and that velocity has a distribution. So that's important. Now, the third thing that I'd like to talk about is you can't get away from polydispersity in multiphase flows. So what you're looking at on the right here is, again, fully resolved DNS past a polydispersed configuration of particles. And you're looking at particle velocity colored in the particle colors are velocity of the particles. The blue ones are very slow. The little ones are fast, right, colored red. And you also have fluid velocity contours here. So the point here is you have a distribution of sizes. And so essentially you have to consider a joint distribution of velocity and size, right? That gives you the complete characterization at the first order of these two effects. So if you put all this together, you'll find that in fact I've ended up motivating the need for Williams's droplet distribution function equation. And in fact, his droplet distribution function first, and then you can always derive the equation from this. So if you have an inhomogeneous time dependent, that time dependence is here, that's inhomogeneous. The first order representation of configurational dependence that comes in the X, joint velocity size is given by Williams's DDF. So if you do anything that is a moment of this DDF, you're not probably going to capture these nonlinearities. That's the point I want to make. So there are some other challenges peculiar to multiphase flows, and one of those is what I call multi-scale interactions. So what happens, here you're looking at a central jet fluidized bed. So what happens is you inject gas through some central jet here. There are particles also injected along with it. And so the particles move up and they may form some sort of contours. Here you're looking at contours of the volume fraction. So if I look at either the number density or the volume fraction, and I try to form a length scale based on that. That's a macro scale length scale, right? So I have a number density distribution in the entire device, and I want to form a macro scale length scale from that. So I could do that by just say n by grad n gives me a length scale of the macro scale. Now it turns out that these particles also have a scale, so that's a micro scale. So the particle diameter is the micro scale. But the difficulty in multiphase flows is that these particles tend to organize into clusters and streamers. And you can actually plot the pair correlation of these particles. So what you're looking at here is G of R is a pair correlation as a function of particle separation. So what is this pair correlation? It tells me that suppose I sit on a particle and I draw a circle around me of radius R, and I say what is the average number of neighbors who would be at that distance R. Okay? So if you see a large peak in the pair correlation, that means that a lot of particles want to be close to each other. And then there is a relative lower probability of finding pairs at this separation and then so on, right? So this gives you a characteristic of structure. So from this pair correlation, you can extract what's called a mesoscale length scale. This is the scale at which stuff dies off and things become more random beyond this length scale. Now the problem in multiphase flows is that these three scales are not separated. Okay? If you look at a liquid, if you look at a single phase flow and you look at a liquid molecules have the same kind of pair correlation. But their length scales are at the molecular scale. So you can analyze using macro scale hydrodynamics, you can use Navier-Stokes. But in a particulate flow, that doesn't happen. So if you're trying to seek a Navier-Stokes-like continuum description of the particulate phase or the droplet phase, like you do in Eulerian 2 fluid models, you're actually violating the continuum hypothesis if those things are organizing in structures like this. So that's a very important point. Now, there are further interactions that are also multi-scale in nature. Now, if you look at drops, so let's suppose we have a driven cavity. Everyone is familiar with this flow, right? You have, say, a square, and then you draw the top plate at a given velocity. As you change the Reynolds number, you'll form a particular structure. If you increase the Reynolds number, you can even form this cute secondary vortex in the corner there. Now, suppose I populated this uniformly with particles, right? So you can see that depending on the Stokes number, particles can get ejected out of this vortex, and they will preferentially concentrate in the high strain rate areas. They would be thrown out of the vortex cores, right? Now, that Stokes number effect is very important because if the flow was turbulent, particles of different Stokes number will interact differently with the eddies of turbulence, okay? So for instance, suppose one were to define a Stokes number, which is a ratio of the particle response time to the fluid response time. I can in fact form a Stokes number for every eddy size L, which has a characteristic time scale. I can form a Stokes number called STL, which is tau p over the characteristic time scale of that eddy. And if I have turbulence, turbulence has a spectrum of eddies, so I'll in fact have a distribution of Stokes numbers, okay? And what we're looking at here is a PDF of the magnitude of gas phase velocity fluctuations. So if you have particles that have Stokes numbers that are greater than 1, they would behave differently from those that are less than 1. Typically, around 1 is the cutoff. If you have less than 1, they will follow the streamlines. If they are much greater than 1, they're inertial and they will depart from the streamlines. So the drop interactions with turbulence are very, very important, and they are always multi-scale. So we have some work in this area that may be of interest, where we try to incorporate a multi-scale interaction time scale for droplets interacting with turbulence. So that's another important challenge when you're modeling multi-phase flows. So to summarize, I've tried to show you that there are nonlinearities in multi-phase flows that are not there in single-phase flows. They arise from the dependence of drag on velocity, from polydispersity, and this I didn't talk about so much because everyone knows that well. There's also two-way coupling. If you do one-way coupled simulations versus two-way coupled, if the mass loading and the momentum loading gets significant, you can have differences in the answers. I talked a little bit about multi-scale interactions, which says that the scale of the structures in the dispersed phase can be important, right? And there's a problem with statistical approaches, which is when you take Williams's DDF, for instance, it doesn't have any scale information. It doesn't tell you how the particles are organized spatially, okay? Apart from it has a number density, but it doesn't have the pair information in it. And then we talk a little bit about drop interactions with turbulence. Finally, there's another very important point is that when you look at this DDF, it's very much close to the kinetic theory of molecular gases, in fact. And in the kinetic theory, one of the cornerstones is an equilibrium PDF. So Maxwellian distribution is an equilibrium. But you know in sprays that the velocity distribution of the droplets is never going to be equilibrium. It's always non-equilibrium. And non-equilibrium problems are much harder to solve because it's much harder to do continuum theory based on non-equilibrium statistics. So if you put all this together, and the point is that these interactions all contribute to phenomena such as droplet clustering, preferential concentration, and these affect performance at the device scale. So they're important. They're not just academic interest. So with all that in mind, I said, what do you want? If you want to build a model and a simulation, what would you like? And here's a wish list. You can add to it if you like, but I think these are the essential ingredients. You need to have a mathematical representation that's capable of representing the physical phenomena of interest. If you don't have the right mathematical representation, you can code yourself till you're blue in the face, but you're never going to get the right answer, right? You need to have an accurate and consistent model for the unclosed terms that you need to model, right? So the accuracy means you've got to validate against something that's even higher fidelity than the model itself. And it has to be consistent in the sense that if there are different ways of representing the same model, they should, and I'll explain that in a bit, they should be consistent. They should also be numerically convergent. You should have a stable implementation. This is very important. For a long time, people have thought that some spray calculations are not numerically convergent. I'll show you that that was purely an algorithmic issue. It's not actually an intrinsic issue to spray models. You need efficient solvers because people want turnaround times overnight in the design world. And then finally, these are things that I don't explicitly deal with, but I believe they're very important to industry. You want to be able to represent complex geometry, and you have to make the best use of computational resources that you, like GPUs and stuff like that. So with that in mind, I said, here's a very busy chart. This is my mental map of how multi-phase flow modeling works, okay? I'll walk you through it, and hopefully it'll make sense. So on the left, you have what I call random field descriptions. So here's a, arbitrary volume in space. These are dispersed phase elements. The rest is fluid. And you start with a color function or indicator function. And this indicator function is 0 if it's a dispersed phase indicator function, 0 if you're in the fluid. It's 1 if you're in the dispersed phase, right? So you know this. This is the basis of all Eulerian two-fluid theory. Goes back to Drew and probably before that Anderson and Jackson, Ishii, all those guys. So you can start with this kind of an approach, and I call this a random field approach, and both are represented in the Eulerian frame. You can also have what's called a point process approach. In this, what you do is you take every dispersed phase element and you assign to it a center of mass, a center location of its center, a radius possibly, equivalent volume, and then there are n of them. And this is what I call a point process approach. Okay, so they're different in that this one has some spatial extent, and this you basically consider points, but you assign them some radius. And the mathematics of these two is very different. That's the key point. This leads you to the kind of Liouville equation that you see in kinetic theory. This leads you to the turbulent random field kind of descriptions. Now, if you start off with the most complete description of this approach, you'll have what's called a multi-point PDF. And if you do the most complete description of the point process approach, you'll have a multi-particle representation which leads to the Liouville equation. Now, the Liouville equation is actually a closed equation for molecules, but it's not a closed equation in multi-phase flows because the acceleration of these dispersed phase elements depends on the fluid phase. And in the point process approach, we have not yet represented the fluid phase. It only represents the dispersed phase. It's kind of a one-sided approach. Anyway, there is an equivalence between these two. You can actually formally show that you can come from here to here. Right. Now, usually we take the Liouville equation. This is too hard to solve. Nobody wants to know the full PDF, joint PDF of all the particle positions and all the velocities. So we do a hierarchy, and you can come down to a 2-particle density or a 1-particle density. The 1-particle density is what is basically Williams's DDF. Okay. You can do the same thing on the Eulerian side, and you can come to 2-point PDFs, single-point PDFs, and there are equivalencies. So if you write a closure model at the droplet distribution function, it means something on this random field Eulerian side. And so when you build a model here, it should be consistent with this model here. Otherwise, it doesn't make any sense. That's something that people have not respected too much in the literature, I feel. Now, from this single point PDF, you can develop moment equations, which is your two-fluid theory, which is what everyone uses as the Eulerian approach. You can take this DDF, and from this, you can perform Lagrangian Eulerian simulations that are basically a simulation approach to solve for this evolution of the DDF. You could also take moments of this DDF and come up with what's called the kinetic theory of gas-solid flows, for instance. Or you could also do what is called quadrature method of moments, which I'll describe in a moment as a way to solve the moments of the DDF. So in a way, what I've tried to do is give you a complete, in one snapshot, encapsulate pretty much what I think is out there in multi-phase flow modeling. Okay? But today, what I'm going to really focus on is that you need to close things at least at the DDF level. If you go down here, I believe you've gone too far. This is too coarse. This is too modeled a level for multi-phase flows. And the QMOM and DDF, I believe, are the minimum level of closure that you need to capture some phenomena. And I'll explain that in a moment. And so naturally, there are some problems when you do moment equations with the two-fluid theory. There are certain phenomena for which you actually need to go up to the 2-particle density, but those models have not gained popularity yet. They're probably still in development, but I think that we may have to go there in the future. Now, on this side, I'm showing you that you couple this usually to a carrier phase. And so you could do a DNS of the carrier phase. You could do LES, large eddy simulations of the carrier phase. You could do RAND CFD. And then you have various flavors of LE simulations. You have people who do Lagrangian Eulerian with DNS in the gas phase, point particles. You may have DNS in the gas phase fully resolved. You could have LES in the gas phase with point particles. You could have RANDs with point particles, et cetera. So this kind of gives you all the combinations you could wish for. So I'm going to compare two approaches. I'm going to compare the two-fluid Eulerian. I'm going to compare the DDF, Williams's kind of Lagrangian Eulerian approach. Now, in the two fluid approach, you only have the mean size and the mean velocity if you do it at the crudest level. Whereas in the DDF, you have the full size and velocity distribution. So obviously, in terms of mathematical adequacy, the DDF beats this hands down. You could do sectional approaches and multi-fluid approaches, and I'll talk a little bit about that. These have a serious problem in that they don't work for crossing jets. I'll show an example how they don't work. And as you saw in the first talk that Professor Raghunandan gave, when you have those atomizers with crossing and offsets, you will see in a cartoon, in a simulation I'll show you very soon, that this just won't work. This approach also has difficulties in the high droplet Knudsen number regime. What do I mean by that? So if you have highly collisional droplets, you can build a theory that's called a low Knudsen number theory, like a Navier-Stokes theory. But if the droplet fluctuating velocities become very small or they're very far apart, they're not very collisional. And they behave more like free molecular gases, like free molecular regime of rarefied gas dynamics if you're out in space. That's a very dilute spray for you. Okay? So in that kind of a situation, this Eulerian approach really breaks down. You won't get right answers with that. In the DDF approach, you have no inherent restriction on droplet Knudsen number or the Stokes number, and it allows for non-equilibrium velocity distribution, which is very important. And then the collisional representation in the Eulerian approach is usually through models, and they're usually kinetic theory-based models that are based on high collisional frequency. But actually, here you don't have that restriction. Collisions are represented naturally. So let me show you an example here. These are two jets moving towards each other, crossing jets example. And this is taken from Kah and Massot and Fox in a flow turbulence and combustion article came out last year. And they were comparing Eulerian quadrature-based moment models for sprays. So if you do the classical multi-fluid model or two-fluid model, Eulerian, what happens is that these two jets come, and at this point what is happening is there are two velocities. There's one stream that wants to go down and there's another stream that wants to go up. It's a multi-velocity situation. You have two streams of droplets with different velocities at the same physical location. In the Eulerian approach, you're going to have only one mean velocity, and that one mean velocity is actually going this way. So the Eulerian two-fluid approach will give you a coalescing delta shock, what's called a delta shock. But the true answer, has been shown by many people using Lagrangian Eulerian simulations, is actually that you will see some penetration of these jets across depending on the collision frequency and stuff, right? So if you use a multi-velocity quadrature model, you can actually capture this crossing jet phenomenon accurately, whereas you can't if you use a single velocity two-fluid model. So I think that's an important thing to bear in mind for all of us who want to do sprays with crossing streams and stuff like that. Oh, thanks. So the outlook for the models, so basically what I'd say is that the kinetic equation or a model DDF is the most promising. LE methods can be interpreted as a solution to that DDF equation. There have been many recent advances in LE methods that show that it's numerically convergent and accurate. You need to use grid-free estimators. This will solve the problem that John was talking about, that you can refine the Eulerian grid independently of the number of droplets if you use grid-free estimators. And if you use computational particle number density control, these are two papers out recently in IGMF, 07 and 09, that you can refer to. Apart from the Lagrangian Eulerian approach, quadrature method of moments by Fox is a very attractive alternative with low cost. In this, in QMOM, the DDF is approximated by a few abscissas and weights, and this is very promising. GPU computing will make these LE calculations increasingly cheaper. For a long time, people have said these are very expensive and not competitive with EE, but I really don't think that's the case anymore. There is, Sean Garrick points out that it would be good to have some uncertainty quantification of these models that we put into these approximate modeling approaches. Here's a map I want to show for multiphase flow simulations. So what I'm doing here is I want to look at simulations by length or time scale. Down here you have atomic or molecular scale. So, and I'm thinking of droplets, particles, or bubbles. I'm going to focus more on droplets, but there are obvious analogies. People have used molecular dynamics at this level to look at droplet vaporization. Single droplet studies come next. And I'll show you some examples of that fully resolved DNS of single droplets. We can look at droplet arrays or clouds. There you would probably look at particle arrays, random fixed assembly suspensions in canonical flows. And then you come to point particle DNS. What I mean by canonical flows are shear flows, isotropic turbulence with droplets in it. And for that, it's useful to look at point particle DNS in some cases. LES, if you want to do slightly more complex geometries. And then, of course, RANs if you're looking at device scale simulations. So I think that's a useful way to kind of look at how, obviously, problem complexity goes up in this arrow. Accuracy and computational costs tend to go up as you go this way. Right? So I'm just putting here a selected overview of people who I think have done things in this area. Molecular dynamics, Mike Michi's group and Mario Trujillo more recently have been doing MD of evaporating droplets. Murad and Law did some collisions between droplets, I believe, a long time ago. John Abraham has done DPD, dissipative particle dynamics, which I classify in this sort of atomistic type of simulations. Single droplet studies, David Schmidt, Brian Hellenbrook, Harry Dwyer has done some stuff. Droplet clouds with point particle. There's very nice DNS by Réveillon from France. LES, there's Josette Bellan, Saurabh Apte, Olivier, Farhad Jaberi, you can see them in this work. Marcus has done very nice work in atomization. I'm sure he'll talk about it. And then LE, you see the Kiva codes came out of Los Alamos with O'Rourke. Rolf Reeds and co-workers have taken that a long way. And John has also done work on this. And then Eva Gutheil in Germany does work with PDF in the gas phase and this. And I've seen some Eulerian calculations by Beck and Watkins for spray calculations. Here's a quick overview of how these comparative assessment of these methods, courtesy Brian Hellenbrook. You can look at ALE methods. They deform the mesh with the interface. You can have higher order FEM with moving meshes started off by Ho. And then you can do spectral element, discontinuous Galerkin. They have high order of accuracy. The problem is remeshing. The cost is you have to remesh every time. If you look at fixed mesh methods, you track the interface on a fixed mesh, impose jump conditions of the interface. In this, you can throw volume of fluid, level set, variance, immersed boundary, immersed interface, ghost fluid. I throw all that in here. They're very, the advancement is basically, the thing we have learned here is don't smooth or smear the interface. That wreaks havoc with your resolution. They're typically lower order of accuracy, first order, but they're faster because you can do the calculation much faster. In this bag, I'm throwing other methods, Lattice-Boltzmann, which has its issues about doing purely incompressible flows. You can't really do incompressible flows in Lattice-Boltzmann. There are some convergence issues there, but they've been addressed, I think. Smooth particle hydrodynamics, MD, cut cell methods, which are hybrids, and then overset grids, the kind of chimera stuff that Harry Dwyer and others do, and also Burton and Eaton have done this. I think the problem with these overset grid methods is where do you apply the matching conditions, and I feel that's a parameter which I don't like hanging around there. These HP finite element methods, Brian gave me a slide here. He shows how you can do edge swappings when you deform droplets, and he gives some, it allows for large deformations and exponential convergence because he uses spectral elements. So I thought I'd share some of that with you. And here's a simulation of deforming droplet that he has done, and I just throw it up there. You can do large deformations of droplets. David Schmidt has also done work like this, Harry Dwyer. And then here's a picture of Marcus's atomizing jet that I pulled out to show you that, this is I believe, some of the state of the art that you're seeing in fully resolved DNS. So LES, this is a spray calculation with large eddy simulations and Lagrangian Eulerian for the droplets from Olivier Desjardins using the NAG solver. There are other people who do LES, as I mentioned, Josette Bellan, Joe O'Flynn, Saurabh Apte, and Farhad Jaberi. And I think this is a very promising approach, and it's really going to be the future. So the outlook for the simulations, I feel, a fully resolved DNS, if it is adequately resolved. A lot of the early fully resolved DNS was not highly resolved, and then you can get wrong answers. So you've got to make sure that you're fully resolved. It's very useful for model development. It's currently restricted to idealized problems. If you go to molecular dynamics, atomistic and coarse-grained simulations like DPD, they're very useful to infer details of physical-chemical phenomena like vaporization, and they can aid model development. If you look at canonical flows, shear flows, channel flows, LES plus LE is very appealing. At the device scale, Eulerian with quadrature method of moments, I think, to solve the kinetic equation is very promising. And what needs to be done, I think for the fully resolved DNS and all this stuff, the more we parallelize, you can extend the range of scales and problem complexity. The utility is in extracting the useful information for models. Challenges for LES and LE and LES and QMOM is developing scalable subgrid closures. And this is very, very difficult for multi-phase flows because in single-phase flows, we assume in LES that the small scales are isotropic, and they are not isotropic for multi-phase flows. We've shown that in particle-laden simulations. If the particles are big enough, you'll get strong anisotropy. The second problem is that in single phase flows, as long as your filter width captures 80% of the energy, you're in pretty good shape and you can move the filter up and down. But because of these mesoscale structures like preferential concentration, in multi-phase flows you can't quite do that. As you change, as you switch across that mesoscale, your subgrid model is going to change. And this is really an open problem, and I think it's a very interesting problem, something that I hope all the students here will pay attention to. We need some bright minds to work on this. And the final point I'd like to make is that when you look at these instabilities in multi-phase flows, they originate at the microscale and then they become large scale. Capturing those instabilities that originate at the microscale is going to be a challenge when you use an LES approach because you're modeling the microscales. Same kind of thing that you get with flames, extinction that you see, you're going to have that same problem. So with that, thank you for your patience. I'll just put up a summary here that tells you what I breezed through. That I'm not going to read out all the points, but I hope that it'll help you digest kind of what I tried to throw out there. And I'm happy to take questions.
Because we are running out of time, we can have only one question.
Okay, I have a very amateur question. I've read quadrature-based solution to Williams-Bray equation, quadrature moment-based solutions.
Yes.
And you did mention that if you have a moment-based approach, then you won't be capturing something. Would you elaborate on what you said?
Okay, so I should be, so I should be careful here about what I mean by moment-based and, so let me go back here to this. So when you're doing moments here, what you do, there are two different, these are two different things. You have an equation, so let's say you have an equation for the DDF. In the moment approach, what you do is you take moments of it, and then you have a lot of terms that you have to close, like the mean drag and stuff like that. In the quadrature approach, what you do is you actually discretize this DDF itself, right? And then you solve for the discretized DDF, okay? So it's distinctly different. So in the moment approach, you're throwing away a lot, the short answer to your question is. And you probably may miss many things. You're not going to get crossing jets right with this approach. In the quadrature method of moments, you are throwing away a little bit compared to the DDF, but you can get crossing jets right. That's why I think it's very promising. It can do multi-velocity transport of fluxes and things like that. So that's why I think that quadrature method of moments is going to be more successful than that one. Does that clarify what?
If you're talking of particle-laden jets, they cross only when you have very, very dilute particle densities.
That's right. That's right.
Okay, so
right.
Effectively, in an Eulerian sense, the viscosity of the particle phase is zero. So there is no stress that the particle phase is existing.
Exactly.
With any high loading of particle densities, you are not going to get particle crossing.
I agree. Right.
And so what you say is the bane of one model could be the boon of the other.
I completely agree. So that's a very good point. So this will work. So the strong applicability is in the dilute regime for these things, and you'll see it in risers, for instance. But if you go into the fluidized bed, the collisional stuff will dominate, and you won't get that problem. I agree with you on that.
Thank you, Professor Shankar Subramaniam, for the excellent review.